Hi guys, now we're going to be focusing most of our energy on building a k nearest neighbor classifier with Python. But then first thing first, what is k nearest neighbor? So this image actually is one of the best way to explain what k nearest neighbor is. So what k nearest neighbor does is it groups after you've trained the model. While training the model, you have to specify a number of k. While training the model, you can't really know what to choose a number of k as, but then I'll show you a trick on how to select that perfectly well, or select the best number of k for your training data set. Now, so looking at this picture here, it has actually classified, after training, it's classified into two classes, class A and class B. Class A is depicted with these stars and class B is depicted with these green triangles. So now a new data set has been imputed for the classifier to predict whether it should go into class A or class B. Now if you've selected your k to be 3, it will select three closest or 3 nearest data points to the new data point, and it will do head count and to choose which class the new data point should be assigned to. And as you can see, if k is equals to 3, it will be assigned to class B, but if k is equals to 7, it will be assigned to class A. Now what we are going to see next is how to build this type of classifier. Basically what I just explained to you is just to give you an overview of what KNN is doing behind the scene. But now we are going to build a KNN classifier. If you want to understand the maths behind KNN, you can actually read up on that. So I'll open my k nearest neighbor notebook that I've created. So what I'm doing here, basically I'm importing the necessary libraries, which I believe you already know about. Then I'm getting my data. I'm working with this audit risk data set, which I got from the UCI data science repository. The link to this will be provided. You can download the notebook and everything from my GitHub account. The link will be below this video. Then we are going to explore and try and look into our data set using df.ed, and after running Alright, so we try to look into our data set using df.ed. Then, because I have actually worked on this data set earlier, I've discovered that the location ID has some issues with it. Why is my laptop taking time to load? But then location ID has some issues with it, and yes, so basically this is it. So this is the head. We can see it has sector score, location ID, and different scores and risks. But then what we want to predict in this case is this risk here, right? This risk. So this is our target. This is our target column, and the rest of the column aside the risk column are all feature columns. Now, as I said, the location ID column has some issues with it, which I'm going to show you now. Because as you know, our algorithm takes in only numerical values, doesn't accept strings. Now, checking the location ID column, you will discover that we have some strings here. We have Safidon, we have Nu, and we have Loharu. Now, what I did here is I just checked for every value in location ID and the amount of times that they occur. So you can see that it occurs 76 times, and the likes and the likes and the likes. Then Safidon occurred 1 time, Nu 1 time, and Loharu 1 time. So I felt they actually did not occur that much. So there is no need for me to be cracking my head on what location ID is, Safidon, Nu, or Loharu. So I decided to drop them. Right. So before I dropped them, I did this. I replaced them with none. I replaced them to be seen as missing values in the location ID column, which I did using the dot replace method And the dot replace method takes in at least 2 arguments. The first argument is what it wants to replace, and the second argument is what it should replace the value you want to replace with. Alright, so what I did here is actually simple. It is I'm just doing some, instead of me to type, what I did here is this. I don't want to type so much, so this is what I did. Ctrl V. Yeah, so if you run this, it is going to give you a list. And this, what this dot split is doing is it is splitting each of this, as you can see, based on the space in between them. If they add comma in between them, right, and then I use the dot split attribute, I would have to specify with a comma here. Then I run, and you see I still get the same thing, but not really the same thing because of this space in between here. Right, there's a space here, there's a space here. So basically, I just want to get what I want. It is used a lot in what I just did here is used a lot in natural language processing, but that is beyond our pay grade here. So basically, that's what I did here, to create a list instead of me to start typing. Instead of me to start doing this, right? Loharu. Then I come and I press comma. Then I do this again for no. I do this again for Safidon. Basically, I just felt I should do that since it doesn't take me so much time to type that out. So that being said, I did that, and as you can see, I used the in place equals to true, which means it replaces it in the original data set. Then I did the drop NA. Remember, I already turned those strings into NA values. Then I do the drop NA, which means I'm dropping them. So after dropping them, now remember this image I showed you that k-nearest neighbor actually bring things together. So you actually want to scale your data set so that they will be between 0 and 1 using the standardized scalar or standard scalar here from sklearn preprocessing. Now this is your first encounter with sklearn. Sklearn is a Python library that is very powerful. This is what you use for most of your machine learning, sklearn or scikit-learn. So you don't mistake. sklearn is the same as scikit-learn. This is what you want to be using for most of your machine learning algorithm right now. So what we want to do here is that we want to reduce the size in between them, because if you check the values we are having here, you're seeing we're having values like 2 point something, 4 point something, 23, and other large values. So we are going to scale them down to 0 and 1, and then before passing them into our k-nearest neighbor classifier algorithm. So the first thing we do here is we import the standard scalar from sklearn preprocessing, and what we do is we instantiate. And what do we mean by we instantiate? We just call the standard scalar. As you can see, we did not put anything inside. It is empty, and basically we are saying, okay, it's an algorithm, but it has not yet been trained, because it's more or less like an algorithm that has not been trained. Right, so now what we do is we fit this standard scalar to our data set without the column we want to predict. That is why we are using the dot to drop here, to drop the column we want to predict. So after fitting the standard scalar to this, it doesn't mean it has already happened actually, because you need to transform it. So the scale feature, which is what you can see here, right, you now still call this same scalar. Remember, this is scalar that we used to instantiate, and then this scalar is what you have fit, which has now learned based on the data. We are now still using that same scalar which has learned based on our data to fit on to transform our data. Remember, we still drop this risk, because if you don't drop it, it is actually going to transform everything. So now we go into this part. This part is not so interesting. We're just creating a data frame. I just created a data frame so you can see what standard scalar is doing. As you can see, it scaled it from negative part and then to positive part. Just bring everything together and to ensure that the spaces in between the values are not so much. We did not specify any argument in our standard scalar, so it scaled it as much as it can. We could have specified that it scaled it to 0 and 1, or minus 1 and 1, and others like that, but most of the time it will scale to what you are looking at here. So that being done, so now we are going to be using our scaled features. Remember, we are going to be using our scaled features, no more our original data set. We are not using our original data set, we are using our scaled features because of what I explained earlier. So we are going to do the train test split. So from sklearn, there's a model called train test split. Remember in the previous video, I talked about you needing to split your data into training and test data. Now, what does train test split do? What is it doing here in this code that has been written here? Basically, what you are doing is that once you run this code, you are going to be getting a value assigned, a data frame object assigned to this value is assigned to all of them, this and this. So we are going to be getting an X train, an X test, a Y train, and a Y test. Now, how is this happening? We use the train test split to split our data. Now, the first thing you input in your train test split is your features, which is our scaled features. Then the column you want to predict, which is the risk column, and then the test size, which the test size, as I said, most of the time you want to split your data based on 70-30. So in this case, you can say 0.3, but then it stands for 30% of the data. So 30% of the data is going to be split. It's going to be split, and this 30% is going to be 70% for Y train and for X train, then 30% for S test and for Y test. Right. So that is that. If you run this, alright, so I'll not be running from here. Sorry for that. Alright, so basically you run that and you get what you want. Now for KNN, now we are now down to our algorithm. Now we just go to our algorithm. So what we've been doing since is basically more or less like preparing our data still. So now what we want to do now is now train our algorithm. So the KNN, we are going to start from k equals to 1. So still the same scikit-learn as I said. We are going to be using this guy a lot from now onwards. You are going to love him. So from sklearn, we import the k-neighbors classifier. Then we instantiate the k-neighbors classifier just as we instantiated the standard scalar. So we call KNN to be equals to k-neighbors classifier, and then you remember now you specify the number of neighbors. This is actually very, very important. I said it earlier that you are going to specify the number of k in the previous video, but then in the algorithm it is called n neighbors. So you specify the number of neighbors. As I said, we are going to be starting with k equals to 1. So the number of neighbors is going to be equals to 1 here, and then we run this. Now remember that when we split our data, I told you we are going to be having the training set and the test set. The training set is used to train your algorithm, and it's the large part of the data set. So you use it to train the algorithm, and as you can see, I've put the X train here, and you also impute the answer, so that the algorithm, while learning, it can see the features, and then it can see the target. Then from there it learns that okay, this is what is affecting this feature and making the target variable this and this and that, and that stuff like that. Everything that happens behind the scene you don't really need to understand. You can go and read up on if you want to understand what's happening behind it, but as a data scientist you don't really need to understand the mathematics. You just need to understand the concept so that you know where to apply which. Now that's been done, what you are going to do here is we are going to now predict the X test. Remember that we have S test here. It is called test because you're actually going to use it to test your algorithm. So now we are going to predict based on our S test. We are going to pass our S test into the same KNN. Remember, it's still the same KNN from here, that is here and then here. So we pass it there, and that being done, we are now going to import all these. These are actually very, very important, and these are what you are going to use to determine whether your algorithm is performing well or is performing very bad. So I'm going to run that. So from sklearn.metrics, you import the classification report. I talked about classification reports in the previous video. Accuracy score, ROC curve, ROC AUC score, log loss. I will not really go through everything, but then I'll talk more on classification reports, accuracy score, and then confusion matrix. So let's move on, because it's going to actually give you most of the information. So what I did here is, you don't mind me, I just decided to play here, but you should actually look through this code and try and understand what is happening. But then what I did here is, I created a function to beautify confusion matrix, because the traditional confusion matrix that comes with scikit-learn is not the best. It doesn't have good visuals. Confusion underscore matrix. I just want to show you how it looks, right? So that you understand what happens. So basically, when you want to check how well your model is performing, let's say based on your confusion matrix, you call what you want to check it based on confusion underscore matrix, and the first thing you pass into it is the correct answer to what it has predicted. And in this case, remember, for S test the correct answers are Y test, for X chain the correct answers are Y chain. And here we have already told it to predict the S test, which you have stored the answers it is getting from this prediction into the as spread. So basically, we are going to be passing Y test into this place first, Y test, and then we'll be calling the pred. I hope you understand. So basically, confusion matrix, the Y test is the answers, which are the correct labels of the target column, and then the pred are what was predicted by our algorithm. So now we want to compare the two of them using the confusion matrix. When I run this, look at what I get. I get something like this, which is really not beautiful. So in light of that, I decided to create my own confusion matrix, which is what you are seeing here. And as you can see, it is beautiful. But then, and it's the same thing, 143 and 143 1. So basically, let me just run through it. So basically, what happened there is that our algorithm classified for 143 times it was correct, for 143 plus 84 times it's classified correctly, and for these other times classified wrongly. So basically, that is the first thing you get from this confusion matrix. And then we move on to the classification report. But then our algorithm actually performed very well. It's just that we can do better, and also I want to show you how you can choose a better k value. So this is what I'm going to do here. I'm going to do this. So what I'm doing here is, I created an empty list. Which I called error rate, and it will take some arguments. So it will save some things into the error rate very soon. So now I'm now saying for I in the range of 1,50. As you can see, I rated that it will take some time. It depends on how large your data set is when you are running this code. But then our data set is not so large, and also my laptop is pretty good. So for I in the range of 1,50, which means we want to try the values of k from k equals to 1 to k is equals to 50. So for I in the range of I, 50 with your colon, to specify you are writing a for loop, we say knn is equals to, remember this, k nearest neighbor classifier, almost the same thing we've done up there, and then the number of neighbors. Now number of neighbors has been specified to be I, because it is going to be changing. Then we say knn.fit the S chain, Y chain, predict this. Then error rate, this is where you should pay attention to. Now the error rate is what is the mean of what the prediction. Remember, this is pred I, the prediction of the algorithm that is not equals to the original value, that is not equals to the actual value of the data set. So basically, we are saying whenever this is not equals to this, it should be noted and the mean should be recorded, and that is the error rate, and we are appending this into this place. So after it does this for the first I, which is going to be 1, it will do it for the second I. Everything here, it will run for the first I, which is 1. The answer will be saved there. The error rate for 1 will be saved there. It will run again for the other, for 2, for 3, for 4, for 5, and the likes like that. So I've run that code, and as you can see, it's done. So what we just do here now is we plot a graph to show our error rate. That's what I'm doing here now. I'm plotting a graph to show my error rate, and now I'm using plt.figure. I'm just specifying the figure size, then I'm using the plot. Now remember, I created with the range of 1,50, so I'm just specifying my x-axis here. Then my error rate is my y-axis. I'm saying the line color, since I'm using dot plot, the line color should be blue. I'm saying the line style should be dashed. That's how you can see that it should be dashed. The marker should be 0 and the marker color should be red. Marker size are 10. Then the title, x label, y label. I run this and I get this beautiful plot. As you can see, our line style is dashed because we specified dashed up here, right? And our marker is 0, and also we have a marker face color which is red. But then that's not what we are concerned about. What we are majorly concerned about is the bouncing around of this ball. And as you can see, our error rate is here, and we want our error rate to be as small as it can be. If possible, we want it to be 0 if possible. So looking at this error rate, we realize that if we're using at 1, we have something around here. But then if we use at 12, we have something very low here. And I think it's almost like the lowest. We don't really need to go ahead and start checking out this. So we can actually try at 12 and compare it with at 1. So this is meant to be 12. At 12, I'll compare it with at 1. You can see that after areas tend to. Okay, I think what happened there was that I did not specify. You cannot really specify. So when you run the algorithm all over again, it gives you something else. Alright, so basically, but we can see from this plot that at 12, the error rate is actually almost at the lowest it can be, because looking at our graph, it never went below this line. All true. So whether I use at k equals 12 or use at k equals 14 or at 22, 23, 24 and the likes, you're still going to be getting almost the same value, almost the same error rate as we got. So now what I'm going to do here is I'm going to run this, and note confusion matrix. I join the confusion matrix, the classification report, and then I am doing this. I am getting the accuracy score. But basically what I'm doing here is I'm saying you print with k equals to 1, give me the confusion matrix with I want line in between for space and another line in between for space, so you can see it very well. Then classification report is y-test, just the same way you do the confusion matrix, you do the classification report, you do the accuracy score, and then the accuracy score is going to give you a number, a value, which you can use to rate the performance of your algorithm. But most of these times, this value which the accuracy score is going to give you might be deceiving. So let's run this. So when we run this, we get our accuracy to be 97%, and that is pretty high. But then this is for k equals to 1, and as you remember, at k equals to 12, it is actually lower. So let's see if it is truly lower at k equals to 12. At k equals to 12. So let me run this, and as you can see, our accuracy this time around is 98%. And also we classified nothing wrong here and only have 4 classified wrong here. So basically you can see the difference. This has 1 here and this has 4 here. This has 0 here and this has 4 here. So that is that. But then one last thing I would like to give you guys before I end this video is yellow brick. Now yellow brick is a kind of metric, a kind of metric visualization library. So it helps you to visualize your metrics very well. So what I did here is from yellow brick. Now before you can use yellow brick, you have to install it. You have to do pip install yellow brick from your command line. So you go to your command line, then you type pip install yellow brick, and after doing that, you wait for it to load, and once it is done loading, So you do pip install yellow brick, and then you run this. But then I have yellow brick installed, so I don't even really need to wait for this. But when you run this, it is going to, you see, it's as you can see, it's already said everything satisfied. Already satisfied. So basically nothing is going to be downloaded, but if they were not satisfied, something will be downloaded. So you should run that on your laptop as well, and then try this code. So what yellow bricks does is just that it's doing a whole lot of work on the background, but then it wants you to just be able to visualize your plot. Now what we want to visualize is the confusion matrix, the classification report, the RSCAEC curve, the precision curve. I'm not going to explain all these things, I don't have time anymore. And then I run this. Takes a little time because I'm actually requesting for a number of stuffs. So as you can see, almost the same thing as what I have here. Remember, I actually built this myself. I wrote the code to display this myself. So, and you can see almost the same thing I have here. And this is k-nearest neighbor, and this is our ROC curve. So you want the area under this curve to be as maximum as possible. This curve here, the green and blue curve, you want it to be. You want the curve to cover as much area as it can. If it's not covering as much area, then your classifier is not good. You want it to probably be at the edge. You want it to be touching this one. You want it to probably form a box. You don't want it to be inside this place. You don't want it to be inside this space. If it's inside this space, then your classifier is not doing well. Your classifier is doing extremely worse if it's inside this other half. And then this one, so we have precision and recall, and this is actually showing, this is actually very, very, very useful, because it is showing you that safe are blue and risky are green. Now it is telling you that out of everything that your classifier, your algorithm predicted as safe, this little one above here were actually risky, but then it called them safe. But then under risky here, as you can see, our algorithm did perfectly well and did not call anything wrong. Right, so that is that for this video. I hope to see you in the next video, where we're going to be talking about other type of classification algorithms which you can use to train your model and see whether you can push up some of the metrics you've gotten. Thank you. I'll see you in the next video.